Part A wants to know what kind of reaction this is, and it's clearly asking that from a redox point of view because it's given you the hint that the oxidation state of oxygen in hydrogen peroxide is -1. It's just worth reminding yourself why that is. If you compare hydrogen peroxide and water, water is typical of nearly all oxygen containing compounds in that the oxidation state is -2, and that's because the oxygen is forming two bonds and it's got more than its fair share of that one, which gives it a -1 contribution, and more than its fair share of that one, so that adds up to -2. Here, if you in hydrogen peroxide, which has this structure, you can see that again the oxygen's forming two bonds. It has more than its fair share of the electron pair that it shares with the hydrogen, so that gives it a -1 contribution. But of course it's equally matched with the other oxygen, so there's no contribution to the oxidation state from that, and so it's stuck on -1. So that's the reason. It's not just a sort of random bit of cheating that we put in to make the numbers balance, but it has the effect that you can see that the oxygen is two lots of -1 in hydrogen peroxide. In water, as we've just seen, it's -2, and of course unreacted elements are 0. So you can see what's happened is that some of the oxygen has gone from -1 to -2, so that's more negative. So I'm going to the more negative oxidation state is reduction, but some of it has gone from -1 to 0, which is more positive, and so that's oxidation. And so the word we were looking for is disproportionation, which, remember, means a reaction where the same element is oxidized and reduced within a single reaction. Part B wants the systematic name of MnO2. So we had this idea of systematic names of inorganic compounds a couple of exercises ago, so this was just a chance to see whether you'd learnt from that one, because hardly anybody got it right that time. But the story, remember, is that if you have a transition element, those can have various different oxidation states in different compounds. So for example, manganese oxide could also be MnO or Mn2O3. There are different possible oxides, and you can't therefore just call it manganese oxide. Commonly it's called manganese dioxide, but that's not a systematic name. The way you do the name systematically is you use the oxidation state of the manganese to specify it. So if you haven't picked up on this idea of systematic names using oxidation states, it's an important thing to learn. So we've got two lots of -2 for the two oxygens, and therefore the manganese must be +4 in order to balance it up, and the name is therefore manganese 4 oxide. And this is being used as a catalyst. So we've got aqueous hydrogen peroxide disproportionating to produce liquid water and gaseous oxygen, and we've got this solid MnO2 catalyst. So when the catalyst is in a different phase from the reactant, you call it a heterogeneous catalyst. So that was the answer that we wanted, a heterogeneous catalyst. And the explanation you give is because it's in a different state from the reactant. Don't just say because it's a solid, because that's not the point. It's not what actual state it is, it's the fact that what the state it's in is different from the reactant. Okay, so heterogeneous catalysis. And then it wanted an explanation of how a catalyst works. It wanted you to provide an explanation based on both an enthalpy profile diagram and a Boltzmann distribution for this. So you had to make sure you did both of those. So the enthalpy profile diagram, we've got hydrogen peroxide aqueous here. Now we've got no information in the question about whether this reaction is exothermic or endothermic, so you basically just have to guess, and there would be no mark for that. So you know, you can put the products down here or level or up there, and it's not going to matter for the purposes of this question. Actually it's exothermic, so let's put it down here, but as I say, that's not the important issue here. So we've got water plus a half O2. What is important to remember is that you label the states fully, including the state symbols. And that change, in whichever direction it is delta H, so that's a negative change. That would be the case if it were exothermic. So then we mark on the pathway that leads from reactant to product, which, remember, requires you to put in energy over and above the normal average energy before you get energy back out again, and that's because you have to start breaking existing bonds before you form new ones. And the height of that hill, starting from here and getting up to the top of it, is the activation energy. This diagram can get very crowded if you're not careful, so it's quite a good idea, I think, you don't have to do this, rather than just marking the activation energy in there, if you just mark these levels and then mark the activation energy over here to make it just a less cluttered diagram. So again, activation energy's got to be a one-way arrow. As soon as you put double-headed arrow on, you're missing the point about that it's the direction going from where you start to the top of the hill is the activation energy. So that's the activation energy without a catalyst. And the point about the catalyst is that it provides an alternative pathway so that you can get from the same state here to the same state there, so these energies don't change, but you can go via a different pathway, and crucially that pathway has a lower activation energy. So what you mark on there now is the alternative pathway, and the idea is this time then that that level is still the same because you haven't changed the energy of the starting state, but now the activation energy, which is the height of the hill, is lower. So this is the activation energy with the catalyst. Okay, so that's what you need to have marked on your diagram. But when it says explain with the aid of, just drawing the diagram isn't enough, because looking at that doesn't tell the uninitiated person why the catalyst increases the rate. So you've got to write a sentence, and the key sentence is that the catalyst provides an alternative reaction pathway with a lower activation energy. But that on its own, of course, doesn't explain why it speeds it up. To do that, you need to wheel Boltzmann in. So then you come to your second diagram, which is your Boltzmann distribution. So remember, for this, you have number of molecules on this axis, and you have energy, or kinetic energy if you like, on this axis. I'm only talking about a single temperature here, so you only need one curve, but it needs to start at the origin, reach a peak, and then come down more gradually on that side, never quite reaching that axis, remember. So that's the sort of shape that you want. Ideally you label those at 0 to make the point that 0 molecules have 0 energy. Now, what the catalyst does, we've already said, is lower the activation energy, so we can mark on two different activation energies here. So this is the activation energy without a catalyst, and the lower activation energy with a catalyst is therefore just going to be here somewhere. So this is the activation energy with a catalyst. And the important thing in relating this to rates of reaction, remember, is the area under the curve to the right of these lines. In other words, the population of molecules with an energy greater than the activation energy. So without a catalyst, that's a small population. Okay, so we can say that the population of molecules with energy greater than the activation energy is increased when the catalyst lowers the activation energy. And you can see that very clearly here, that because you've got a lower activation energy, the area here, which represents now the population of molecules with enough energy to react, is a lot bigger. So the population of molecules with energy greater than the activation energy is increased when the catalyst lowers the activation energy. So the probability, or frequency is a good word to use, the frequency of successful collisions increases, and therefore the rate increases. Again, it's about spelling it out. Don't just say the frequency of successful collisions increases, because I'll say, yeah, so you have to spell out what that means. Therefore the rate of reaction increases. Okay, so that's the whole catalysis story. Usually you'll be asked for one or other of those diagrams, but actually it's really only when you put both of them in there that you get the full story.